standard, if you have 2 points in two-dimensional plane, then you can draw a line connecting to these 2 points. So similarly, in interpolation, what we do if we have n plus 1 data point set, like here you can see we are starting from x naught, y naught, and this is x and y n. So we have with us n plus 1 data points, and we are trying to find a curve that best approximate this data. And this thing is known as interpolation. So in interpolation, we are trying to find a polynomial through various methods which best fits this data. In this, we have like a Lagrange interpolation formula. Then this is the formula for Lagrange interpolation. Then Newton divided differences formula, and many more. But before this, we have to learn some basics of finite differences. So what is finite differences? So we have like this. If we have like this x naught, y naught, x n, y n, and this n plus 1 data points. So if these are like xi's, x naught, x1, and xn, if these xi's are equally spaced, if these xi's are equally spaced, then we say that interpolation for equally spaced points. So what we mean by equally spaced? This xi plus 1 equals to xi plus h. That is the difference between the two consecutive values of x is remain this h. So if you the difference between the two consecutive values of x remains same, then it is called equally spaced data. So you can see here from this equation, xi plus 1 equal to xi plus h, I goes to 0, 1, 2 up to n minus 1. So you can see that the difference between x1 and x0 is h. Similarly, x2 and x1 is h. So this kind of data is known as equally spaced data. So first we learned some operator known as finite difference operator. So the first one is our forward difference operator. So the forward difference operator we denoted by this del. So this delta, this upper triangle, is known as first forward difference operator, and the definition of is this: if you have any function of x and you are applying a operator delta, so delta of f of x is equals to f of x plus h minus f of x. So this is the definition of forward difference operator. And then we have this another operator called nabla, that is that this reverse triangle. So this is known as the first backward difference operator, and it is defined like this: f of xi is equals to f of xi minus f of xi minus h. Then we have this central difference operator, and then we have this shift operator. So first we learned this these difference operators. So for this, we will start from here. So finite differences, I think this is again visible to everyone. Yes. Okay. So suppose you have a function y equals to fx, and this one actually unknown to us, this fx, but we have equally spaced data. So I already discussed with you what is equally spaced. That is the difference between the two consecutive values of x is h. You can see x naught, x plus h is the next data, x plus 2h is the next to next data, and x plus nh. And these are the y's. So there is no relation between yi's. So only these xi's are if equally spaced, we say that it is equally spaced data. And we have to determine the form of this function. Sometimes like we want to know like if we have this n plus 1 data points, so what is like if you have n plus 1 data point, like you know that the value of the y at x naught is y naught, and the value of y at x naught plus h, that is x1, is y1. So if you want to know what is the value of x some random points, so if you want to know the value of x other than these n plus 1 points, so you require the form of fx. So with this given data set, we generate some function of fx, and then we can substitute any random value of x, and then we will get its value. So once we get the form of x, we can calculate its derivative also, and the value of the derivative, some unknown intermediate point, that means other than these n plus 1 point, because these n plus 1 points are already with us. So for to create some these kind of polynomial, so we required some basics of differences, like these forward differences. So I already told you the definition of forward differences is like this. If you apply delta to any function, you have to write like delta of fx equals to f of x plus h minus f of x. So you use that definition and you will get the value of first forward of y naught. Similarly, first forward of y1. Since in this we have n plus 1 data points, so we calculate all these forward differences in the form of tables. So, and this table is known as forward difference table. So forward difference tables means you write all the x, like this is x naught, this is x1, this is x2, and this is x3, x4, x5. So these are your xi's, and the corresponding yi is also given to you. And now you have to calculate what is the first difference. So if you like the definition of so this is the you can see this is the definition of first difference operator. Delta of f of xi equals to f of xi plus h minus f of xi. So whenever you apply this delta to any fx, it will add like f of xi plus h and then minus f of x. Similarly, like instead of if I substitute x naught, I will get first forward of f of x naught is equals to f of x naught plus h minus f of x naught, and that is f of x1 minus f of x naught, because x naught plus h is my x1. So f of x1 minus f of x naught, this is actually first forward difference of f of x naught. Similarly, first forward difference of f of x1, in this formula, if I substitute I equals to 1, it will be like delta of f of x1, f of x1 plus h minus f of x1. So whatever argument is there, we add the common difference h and then f of minus f of x1. And we know that if x0 plus h is x1, and then x1 plus h is x2, because x1 itself is x0 plus h, so it's finally like x0 plus 2h, and then it is x2. So f of x2 minus f of x1. And in the sometimes we denote this f of x1 by y1 and f of y0 by y0. Similarly, f of x2 by y2 and f of x1 by y1. So here like this, you can see here this one. This like f of x0 plus ih, we representing by f of yi. So if it is x1, it means that x0 plus h, that is x1. So f of x1 is y1. If it is x0 plus 2h, it means f of x2, and it is y2. Similarly, some author use this fi notation also. f of x naught plus ih is fi. So, and you have to remember these kind of terminology, like if we have f suffix I and we have equally spaced data, so then this f suffix I is representing this f of x naught plus ih. So this is f of x naught plus ih, or I can write like f of xi, because this x naught plus xih is actually our xi. This is the way we have defined our equally spaced data. So equally spaced data, we mean by the equally spaced values in the x argument, and this xi is x naught plus ih. So if xi is x naught plus ih, then it means yi is f of xi, and fi is also, this can be also written as. But if you find, like, because we also going to learn the central difference operator, and where there we have these kind of indexing. So yi by 2 means f of x naught plus I by 2 into h, and yi plus 1 means f of x naught plus I plus 1 h. So from here you can think this as a formula, and whatever way you shift the I, the formula will change accordingly, like I by 2, then here it is I by 2, and if it is I plus 1, then it is I plus 1 into h. Similarly, in terms of the f notations. So the common, like here you have x naught y. Sometimes this is the way we represent data, like this is the n plus 1 data, because we are collecting a set containing n plus 1 data points, I ranging from 0 to n. It means n plus data point set you have, and you are claiming that they are equally spaced. Equally spaced means that the variable x defined like this, xi equals to x naught plus ih, and this h is known as the common difference, that is this one. If you take any two consecutive values and you calculate their difference, you will get the h, and the h remain the same. And then you have defined in terms of the variable y. So y is actually f of yi is actually f of xi, and this is actually xi. From here you can see xi is x naught plus ih. So this kind of notation we will use. And then we have our first difference operator, that is known as delta, this triangular shape. And then we define the first order differences. So you have to notice this thing. I'm writing here first order. It means I'm applying delta to one time to any function fx. So this is the function fx, and I am applying the delta operator to the left of it. And this also you have to remember, like operator is always on the left, and this operand on the right. So this is the operator delta of f of xi is equals to f of xi plus h minus f of xi. So this is the way you have to remember it. The definition of first forward difference is delta of f of xi is equals to f of xi plus h minus f of xi. In particular, you have substituted the value 0, you will get this f of x naught plus h minus f of x naught, which is f of x1 minus f of x naught. And in particular for x1, we will get f of x2 minus f of x1. So in general, because sometimes in some books you will find the y in terms of x. So what is delta of yi? Because I know that yi is actually f of xi. So if yi is actually f of xi, so it means here y of xi plus h, and what is xi plus of h? Xi plus h is actually xi plus 1, because if I am adding xi by h, I will get xi plus 1. So f of xi plus h, f of xi plus 1, it is y of I plus 1, and f of xi is yi. So this is the another way to remember, and you have to keep both of them in your mind, that first forward delta of yi is y of I plus 1 minus yi, and in particular for 0, delta of y naught is equals to y1 minus y naught, delta of y1 is y2 minus y1. Then we have the second order forward differences. It's like differentiation. But we have here, instead of continuous data, we have discrete data. So for discrete, to handle discrete kind of data, we require this forward difference operator. So this is the first and this is the second. So the second order forward difference means we are applying one more time delta to this f of xi, delta of f of xi. So that is two times applying delta to f of xi, you will get the second order differences of the function f of xi. So you know that if I apply first time delta of f of xi, by the definition this, it is actually this one. And then this delta, then this delta apply to both of them. Delta of f of xi plus 1 h minus f of xi. So this delta is applied here also and here also, and we will get this delta of f of xi plus h minus delta of f of xi. But we know that delta of f of xi is this one. So it means delta of f of xi plus h is equals to this only, is equals to f of xi plus 2h minus f of xi plus h, and this is equals to this one, f of xi plus h minus this single term is equivalent to this one, and this single term is equivalent to f of xi plus 2h minus f of xi. You can see here. So the first term is equivalent to this because I applied the delta operator to f of xi plus h, and this is delta of f of xi. And if I simplify them, I will get f of xi plus 2h. This is minus and this is minus 2 of f of xi plus h and plus f of xi. So the second time operation of forward difference operator delta on f of xi will give us this formula, f of xi plus 2h minus 2 f of xi plus h plus f of xi. In a similar way, we can see for yi also. So like yi delta of yi, then yi plus 1 minus yi, and then this delta distributed over these two terms, you will get this one. And then again you use the definition of delta to yi plus 1, you will get this one, and for delta for yi you will get this one, and finally after simplification this is in terms of y. So delta 2 of yi is equals to yi plus 2 minus 2 yi plus 1 plus yi. In the same way, we have another operator known as backward difference operator, and we define it by nebula. This is the notation to represent nebula. And then we say that what is the first order backward difference. So the first order backward difference is this one. Delta of f of xi is equals to f of xi minus f of xi minus h. And then delta of xi plus n delta. Okay. So you can see here, when I'm defining this forward difference operator, delta of f of xi is f of xi plus h minus of f of xi. Okay. So it means if I write here instead of I, if I write n here, so I cannot calculate. I am not able to get the value of delta of f of xn, because delta of f of xn means xn plus h, and I don't have the value more than xn. So it means I can calculate only values up to x for this forward difference values for f of x of n minus 1 only. So like if we want to calculate the value near the initial values of the data, like if I want, this is the data like x naught fx1 fx naught x1 fx1 and xn fxn, and if I want to know the value of fx near to the point x naught, then I use the forward differences formula. But sometimes I want to know the value near to the xn, that is xn fxn, so I use the backward difference operators. So now we define again this backward differences, that this nebula of f of xi is equals to f of xi minus f of xi minus h. So you can see the definition difference. Earlier we are adding some xi plus h here in forward, but in backward we are writing directly the value f of xi as it is minus f of its previous value. And here I can calculate the backward difference operator of f of xn also. Like f of xn, it is f of xn minus f of xn minus h. So you can see f of xn is equals to f of xn minus h, and xn minus h means xn minus 1. And in particular for x2, it is f of x2 minus h, and then f of x2 minus f of x1. And similarly, you can calculate backward of f of x1 also, but you are not able to calculate backward of f of x0. And then similarly in terms of the y also, like backward of yi is equals to yi minus 1, backward of yn is equals to yn minus 1, backward of y2 is equals to y2 minus 1. And some author defined this in this way also, like backward of f of x plus h equals to f of x I plus h minus f of xi. Because when we are applying backward, we are writing directly the function at xi and then minus value of f at xi minus h. So, but here it is xi, instead of xi we have xi plus h. So backward of f of xi plus h is equals to f of xi plus h minus f of xi. But here you can notice one thing, f of xi plus h minus f of xi we are getting. And if you see the forward difference, this is this one, f of xi plus h minus f of xi, it is forward of xi. So we can see that backward of xi plus 1 is equals to forward of f of xi. Again, we have second order backward differences also. The second order backward difference is again applying 2 times of Nebula operator to f of xi. So one time operation will give you this one, f of xi minus f of xi minus h, and then you distribute this delta to each of these values, you will get this one. And then you apply the definition of this nebula. The nebula of this will give you this one, and nebula on this will give you this one, and after simplification you will get this one. So the second backward of f of xi is equals to f of xi minus 2 f of xi minus h plus f of xi minus 2h. Now we have another operator known as shift operator. So how we define this, like they denoted by e, and if we apply this operator to any function fx, it will give us the next value, function value at the next point, like e of f of x is equals to f of x plus h. So this is the definition of shift operator, that is shifting the value of the function to the next point. E of f of xi is equals to f of xi plus h, like e2 of f of xi is equals to e of f of xi, and then again applying this, but one time application of e will give us this one, f of xi plus h. And then we know that if we apply one more time e, we have to add one more h here. If we add one more h here, this plus h, we will get f of xi plus 2h. And in general, k times application of shift operator to the function fx will give us f of xi plus kh. And we have also this inverse operator, like e minus 1 of f of xi is defined by this, f of xi minus 1 h, and then e minus k f of xi is f of xi minus kh. So this is the way we define our shift operator. Then we have this central difference operator. We denote it by this this delta, and this delta, and then we apply this f of xi. So it will give us the formula of the central difference operator delta is like f of xi plus h by 2 minus f of xi minus h by 2. So this is the way we define central difference operator. So in particular, if I write I in place of 1 in place of I will get this. Central difference operator of f of x1 is f of x1 plus h by 2 minus f of x1 minus h by 2. And if I apply this to this value, fx, in general, we apply this delta central difference operator to this kind of values, f of xi plus h by 2. This kind of value, we generally use the central difference operator. So if I apply this like this value as it is plus h by 2, this value as it is minus h by 2 as per the definition of central difference operator, and I will get this one. So here you can see again this central difference operator of this value is equals to f of xi plus h minus f of xi, and this is actually the forward difference of f of xi. So this central difference operator delta of f of xi plus h by 2 is equals to this f of xi plus h minus f of xi. And then we have another operator like okay, we take some values like this one. So like y delta of y1 by 2. So like y1 by 2 means y1 by 2 plus 1 minus y1 by 2 minus 1. So y1 by 2 plus 1 is y1 and y1 by 2 minus 1 is 0. So y1 minus y0. Delta 3 by 2 is 3 by 2 plus 1 by 2 is 2 and 3 by 2 minus 1 by 2 is 1. So in terms of y, this is defined like this. Then we have another operator known as average operator, and we represent this by mu. Mu of f of xi is 1 by 2 f of xi plus h by 2 plus f of xi minus h by 2. Now we calculate the relation between these five operators: delta, nebula, e, this, and mu. So we know that from the definition of delta, delta of f of xi is equals to f of xi plus h minus f of xi. But from the definition of this shift operator, f of xi plus h is equals to f of xi. ये जो minus है, this one actually minus, not underscore. So this is actually minus. So f of xi plus h, I write e of x, f of xi by the using the definition of shift operator minus this f of xi as it is. And then I take this fxi outside and it's becoming new operator e minus 1. So I get the relation, the delta is equivalent to the operator e minus 1, or e equals to 1 plus delta. Then we have this nebula. We know that this nebula over f of xi is equals to f of xi as it is minus f of xi minus h, f of xi, and this is again from the definite inverse shift operator. We can write that f of xi minus h is equal to e inverse of f of xi, and then again I take this f of xi outside. I will get 1 minus e raised to power minus 1, and this is the relation between nebula and the shift operator, this one, and this e inverse is equals to 1 minus nebula. Then the relation between the shift central difference operator and shift operator. We know that from the definition of central difference operator, this of f of xi is equals to f of xi plus h by 2 minus f of xi minus h by 2. But again, this can be rewritten as by using the definition of shift operator like this, and then we take this f of xi outside and we'll get this is the relation between central difference operator and shift operator. And in the similar way, we have the formula for or relation between the average operator mu and the shift operator. Now we will see some properties of the central difference operator delta. The forward difference of a constant function is always 0. So we will see this one like we have some function fx and whose value is c for all values of x. and suppose h is the common difference. Now you apply the first forward of fx. But you know the definition of forward difference is f of x plus h minus f of x. And since fx gives the value c for all x, so whether x is x or whether x is something x, the value of this is always c. So because the function is a constant function for all argument x, so instead of x, if we have x plus h, the value remain the same c. So it is like c minus c, and you will get 0. So if you have some constant term, then therefore constant function, then the first forward or any forward difference is always 0. So the forward difference of a constant function is always 0. Now if you have two functions fx and gx, and then you can apply your forward differences to this, then it is actually forward of fx plus forward of gx. The proof is simple, like this is forward of fx plus gx, and from the definition is whatever is here, we write the value of this thing at the new variable x plus new argument x plus h, that is this one, f of x plus h plus g of x plus h, and then minus this thing as it is, and then we rewrite this with this and this with this, we'll get these two kind of terms. And then this one is actually, by the definition of forward difference, it is the first forward of fx plus first forward of gx. So if you apply the first forward difference to the sum of two function, you will get the forward difference of first function plus the second forward difference of second function. Similarly, like you have two constant a and b, then the a fx plus b gx is equals to this. Delta of a fx plus b gx is equals to a into first forward of fx plus b delta gx. The proof is simple. Again, like if you have two function f and g, then the like forward difference of their product is equals to this: g of x plus h first forward of fx plus f of x first forward of gx. And if you have like fx and gx and they are in creating some rational function, then the first forward is g of x delta of fx minus f of x delta of gx upon g of x plus h into g of x. So this theorem we will discuss later. Okay. So here, like I will tell you how we create the tables. Okay. So now from the beginning, I am telling you the data is equally spaced. So you can see this data. Like for x0 we know y0, for x1 we know y1, for x2 we know y2, for x3 we know y3, for x4 we know y4. And if you see the x values, the what is the common difference, you can easily guess it is 2. Like from x1, if you differentiate these two consecutive values, x3 minus 1 you will get 2, 5 minus 3 you will get 2, and 9 minus 7 you will get 2. So this data is equally spaced because its x variable have the common difference h between any two consecutive values, and the corresponding y data is also with us. Now to calculate the forward difference table, because we required this forward differences, first order forward differences, second order forward differences, third order and fourth order forward differences. So what we do, we write these x and y data in the format of column, like x in the one column and y is another column. And we say this is x0, x1, x2, x3, x4, and the corresponding value we say y0, y1, y2, y3, y4. Now if I told you to find the first forward of y0, so what is the formula? If you remember, the first forward of y0 is y1 minus y0. Like to get the values of the third column, we just simply difference this y1 minus y0. Like 13 minus 11 we do, and we will get the first forward difference of y0. Now what is the first forward difference of y1? It is y2 minus y1, because the definition is like delta of y1 is equals to y of I plus 1 minus y1, that is y2 minus y1. So this is y2 and this is y1, you will get easily 3. Then first forward of y2 is 20 minus, because it is y3 minus 4, and then delta of y3 is equals to y4 minus y3, you will get 6. Now to get the second order difference, what we do, like second order difference, delta of y0 is equals to simply these two values subtract. 3 minus 2 you will get 1, and 4 minus 3 you will get again 1, and 6 minus 4 you will get again here 2. And then the third forward difference of y0, you will differentiate these two, you will get 0. And then third forward of y1 is 2 minus 1, you will get 1. And fourth forward of y0 is 1. So here you can see that I have underlined these values, because if we are creating the forward difference table, then these values are important to us. And like it is, if this one is y0, the first value of this column is first forward of y0, and this is the second forward of y0, and this is the third forward of y0, and it is the fourth forward of y0. And if this is y1, the below value, it is first forward of y1, then second forward of y1, then third forward of y1, because we are not able to calculate the fifth forward of y0. Here y2, so like this we represent the data. And this, okay. Now we again back to this. So we have already discussed this, and we have defined this like the first forward of yr is equals to yr minus yr plus 1 minus yr. So here this is the table of, this is x0, x1, x2, x3, x4, x5. This is y0, y1, y2, y3, y4, y5. So the first forward is delta of y0, and it is the difference of these y2, y1 minus y0. First forward of y1 is y2 minus y1. Say first forward of y2 is y3 minus y1, because what is the definition? First forward of yr is equals to yr plus 1 minus yr. So instead of r, if I substitute 0, it is first forward of y0 is y1 minus y0. First forward of y1 is y2 minus y1. So like this. And to get the second forward of this yr, actually I apply this delta one more time here to this equation. So if I apply delta both sides of this equation, on the left I will get delta 2 of yr, and this delta is applied to here. So to get the, like, this is again a new formula, this one. If in this formula, if I write y delta 2 y is not, that is r, if I replace by 0, so delta 2 of y0 is delta of y1 minus delta of y0. So to get the delta 2 of y0, actually from this formula it is delta y1 minus delta y0. Delta 2y1 is delta y2 minus delta y1. From here you can see, because if I write r equals to 2, it is like delta 2 of y2 is equals to delta of y3 minus delta of y2. So this is, so difference of these two will give this value. And now to get the next value, in general I am writing this formula like a pth order difference. So pth order difference of yr is equals to, it's p minus 1th order difference of yr plus 1 minus p minus 1th order difference of yr. So similarly, the delta 3 of y0 is equals to this minus this. and delta 4 of y naught, this minus this. Now we go to this backward difference. So one thing you observe here in backward difference, what is the formula for backward difference? If you remember, they have written here. This is the formula for backward difference. Delta of YR is equals to immediately value of YR minus its previous value. So delta of YR is equals to YR minus 1. So if here, instead of R, if I write 5, so what is delta of YR? 5. What is delta of Y5 is Y5 minus Y4. You can see delta nebula of Y5 is Y5 minus Y4. If I write एक्चुअली ये इसमें गलत लिखा है, नेबला है, दिस बुक में भी गलत हो गया, ये एक्चुअली नेबला है. So nebula of y4 is equals to, like if you substitute here 4 in place of r, so nebula of y4 is equals to y4 minus y3. So this minus this. Nebula of y3 is y3 minus y2. Nebula of y1 is y1 minus y0. So the value will be the same, but their interpretation is changed, because earlier here I am writing delta of y0. Now I am writing nebula of y1, and the values I am calculating in the same way, y1 minus y0. Similarly, now it's like in backward difference table, these values are important to us, these. And the value in the forward difference table and backward difference table, you will get the same value, but their interpretation is changed. If we are dealing with backward difference kind of formula, it is actually delta of y1, but in forward it is forward of y0. So like this. So again we back to this. So you can see that this we have already discussed. This is the table, and this is its forward difference table. Now this is the backward difference table. So in backward difference table, I am writing nebula of y1, but it is again y1 minus y0. You can see here. Here also I calculated y1 minus y0. When I am using forward difference table, in forward of y0 is again y1 minus y0, and forward of y1 is y2 minus y1. But similarly, in when we are using backward difference table, delta of y1 is y1 minus y0. So the value will come same, but interpretation is changed when we are saying backward difference table and when we are saying this forward difference table. So you can see, I think it's a different data. So here we have again x and corresponding y. Here you can see that the common difference between the consecutive values of x is 4. So it's the equally spaced data. And this is xi, this is yi, and now you are calculating nebula of y1. So how this is defined? y1 minus y0. So y1 minus y0 means 16 minus 13. Earlier we are doing the same calculation, but there we are writing delta of y0, but as it is a backward difference table, we will write backward of y1. It is 3. Backward of y2, again 4 minus 3, it is 1. Backward of y3, third time backward of y3, it is 2 minus 1, you will get 1, and the fourth backward of y4 is 1. So earlier in the previous table, I am focusing on these values because this one is these kind of values, because this is the forward difference table. Now I am dealing with the backward difference table. So these values are important to me. That's why these values are bold. So it is y4, then delta of y4 is important to us, delta 2y4, delta 3y4, and delta 4y4. So in backward difference tables, these values are important to us. And if I calculate if I having the same data and if I calculate the forward difference table, the value remain the same: 13, 16, 20, 26, 36, 3, 4, 6, 10, 1, 2, 4, 1, 2, and 1. but their interpretation is changed. Here delta y naught, here delta 2 y naught, here delta 3 y naught, and here delta 4 y naught. So the value is same, but the interpretation is changed when we are saying it's a backward difference table and when we are saying it's a forward difference table. Because when we are developing the formula to generate polynomial to represent this data, and the examiner or someone asks you us to find the value of y near to 17, value of y when x is 17, so you have to apply your backward difference formula, then you have to create your backward difference table. And if I told you to find the value in like if this kind of data we have, and if I told you to find the value of x equals to 1.1, so nearer to x naught, then I have to use the forward difference table, and I have to apply the forward difference formula, and then these values are important to us. And in the same way, someone asks you to find the value near to the value, this middle value, x equals to 5. Like if someone told you to find the value of y near to 4.5 or 5.1, then we have central difference table also and central difference formula also. But you can see like delta of y1 by 2, like central difference table I am going to create. So I know this is my x, this is my y, and delta of y1 by 2 is equals to y1 minus y naught. Again in the table we are doing the same thing, y1 minus y naught, but the interpretation is changing. Delta of y1 by 2, y2 minus y1, delta of y3 by 2, but the interpretation is changed. So the value are same, but the interpretation is changed according to our requirement. Like if someone is asked the value near to the x, then we write the table in the form of central difference table, and then these values, when we are dealing with the central difference table, then these kind of values are important to us. So here we have created the central difference table for this data. Again, this data is equally spaced with common difference 3. So this is x, this is y. And again, we are doing 14 minus 10, we are getting 4, but this is delta 1 by 2, y1 by 2, because this is y1 by 2, it is the definition is y1 by 2 plus 1 by 2 minus y1 by 2 minus 1, that is y1 minus y naught. This y3 by 2 is equals to y3 by 2 plus 1 by 2 minus y3 by 2 minus 1 by 2, that is y2 minus y1, you are getting 6. So this is the way. Then we have this we will discuss in next class, Newton forward difference interpolation formula. So you can see that this is a forward difference interpolation formula, and here we are using forward operators. In the same way, we have backward difference formula also. I think it is not in this slide. Okay, I stop here. And we will do some uh, calculation in the next class. So, and again, I'm giving attendance to all of you. And tomorrow you attend, because tomorrow we will like this concept I already discussed with you. Not tomorrow we will do some numerical calculation, and in tomorrow class I will told you to create some forward backward difference table, find shift operator, and the solution you have to WhatsApp me immediately in the class itself. So I think one more thing, like do you know when is the midterm exam? Any one of you?
Yes, sir. It's 27 September to